So we kind of left off in the middle of mutable references yesterday. It was a bit of a teaser. I don't have enough on the board right now, but let's just kind of get back to where we were. Okay, so what we were talking about was the addition of mutable references to our simply typed lambda calculus, right? So now we have types in addition to bool and tau1 arrow tau2, we had added this type ref tau, which is supposed to be the type that we ascribe to something that is a reference cell in memory. And when we create such a cell, we initialize it with a value v of some type tau, and then it must, our language ensures type preserving updates, so that cell must always forever in the future contain a value of type tau, right? So type preserving updates is something we talked about. We also talked about the fact that in this language, even though it's just simply typed lambda calculus, and all we've done is add references, we can now create cycles in the heap using that Landon's knot trick, where you initialize a cell to some unitary unit function, and then you can update the cell to put in a function that just refers to itself. So it keeps calling itself, and it went into an infinite loop, right? So we have non-termination in this language and cycles in the heap. Okay, so type preserving updates. I also told you what strong updates are. They're sort of the opposite of type preserving updates, where you can change the type, but that's not what this language had. All right, we talked about the operations in the language that we added are new, read or dereferencing, bang, e, and assignment. And just for reference, and we talked about the operational semantics, but just for reference, I will put the typing rules on the board, because that's going to be relevant. Everything else, I guess, we talked about yesterday. So if we if we do new, given an expression e of type tau that we're going to evaluate and then initialize the cell with, we get back a reference of type tau. When we try to read, if e has type ref of tau, then bang of e or dereference of e will have type tau. So this is how we read out of a cell. And then finally assignment, right? E1 gets E2. Here we require E1 to be a reference of type tau. And the only type of value that we can update the cell with has to be something of type tau. Let me put it over here. E2 must be of type tau. Okay, so these taus must match. And I sort of arbitrarily chose to have assignment return the unit value. You can have it return a location or the value stored in the cell, et cetera. But this is what we're doing. Okay, so type preserving updates. And then we were talking about how would we change the logical relation, the semantic model that we've constructed so far, in order to accommodate, in order to give a meaning to, this reference type, right? So that we can prove soundness of the extended language. Okay, so I had introduced a few things. I'd said that, what we already have with our step index model is something I call a possible worlds model. But now I was trying to motivate how we need richer worlds in this setting, because now we basically have a step relation, right, that takes a store and an expression. This is our abstract machine, and it steps to some other x prime, e prime. That's the general shape of reduction of how programs run in our language. These stores are mappings from locations, let's say L1 to V1, L2 to V2, et cetera, right? It's just it's a finite map from locations to values, right? That's our memory or our store. And that is going to change over time as you run your program, right? So when we start to ask this question of when does a location belong to or look like it has the type ref of tau, we ask this question of like, all right, how do we use this location? How do we use things of type ref tau? And we know we use them by reading out of them and by updating them, right? And so for reading out of them, you guys suggested that one of the requirements we need is that when we look up the value stored in this stored at location L, we better get something that behaves like a tau, right? That seems intuitively like just the right thing, and it will make things work for this rule, in a sense, right? Because this is how this is reading out of a cell. Now, for writing into a cell, we were talking about the fact that this doesn't say anything, right? And I just want to pause there for a second. I had introduced this idea of, well, if we want to make sure that we always, as the program runs, as we go from our current world into future worlds, we want to make sure that every single location keeps containing values of its original type, right? Location's initialized, we decide it must contain something of type tau. That location should always contain something of type tau, right? Some other location contains value of some type tau prime. That must always contain values of type tau prime. So to ensure this condition, I'd like to keep around a memory of what those types are. And we're going to do that with a store typing. So instead of putting an S there, I'm just going to short circuit that, and I'm going to show you how I'm going to bring the S condition back in a little bit later. But for now, I'm going to say that's enough for me to just remember that, remember this store typing, okay? I could do this a different way, too. I could say, oh, yeah, let's keep our S there, and let's add the psi, and you can see why I need both, right? Actually, let's do it that way. We'll just do it a little slower. So we already have this condition, and we're saying that if you read out of something, the value that you read out of the store should behave like a tau. I'm not bothering with the worlds right now. We'll get more precise in a minute. I'm trying to get the overall intuition. But then we have this other condition that this location is one that will forever contain a value of type tau. How do we say that? We say, well, the current world is telling us that this location should have something of a certain type. So this psi is going to be, just like the store is a mapping from locations to values, the psi is going to be a mapping from locations to things of this shape, semantic types. So L1 could be tau1, L2 could be tau2, but they are the semantics of types, not syntactic types. Okay? All right, so if this is what our store typing is telling us, it's a semantic store typing, then here I want to say that L is a location that will forever contain values of type tau. So to say that, all I need to do is go look up what size is telling us about what types this location is allowed to contain, and just make sure that whatever that type is, whatever v tau this gives us back, that is equal to the interpretation of this exact tau. Now, modulo the well-foundedness issue, if we could say that, we'd be golden. Okay? That's what we want. And now let me talk about, I answered a whole bunch of questions at the end, like we were here for like 40 minutes, and I told some of you some extra stuff, but let me tell all of you all of that stuff. Remember we had a monotonicity property up on the board when we were talking about just step index logical relations, right? Let's go put that back up. Because our worlds are richer now, okay, so the monotonicity property says, it's a lemma we had to prove. It says that if some value v belongs to or behaves like a type tau for k steps, then for all j less than or equal to k, v also behaves like tau for j steps. And the way that I want you to read this is to say, if v behaves like tau in the current world, then in all future worlds where we have fewer steps left, v still behaves like a tau. I'm treating those step numbers as worlds, right? But what I'm talking about now is that I want to generalize what my worlds, the information that my worlds contain. I have to generalize it. I have to keep more information around, right? Now my world is not just a k, it's a ks psi. All right? So basically, if it was just a ks, right? If we weren't keeping around the store typing, I think this is like something interesting to say. And then we wanted to prove monotonicity, but our worlds just contained, I'll write it like this. Prime. So suppose we could just go with our original definition, where we have number of steps left and a store, but we don't bother with the psi. I want you to understand what will go wrong. What will go wrong is that so we don't have this condition either. We only have this. So when we read out of it, we get taus. Great. The problem is, this is still a possible worlds model. And at some point, just like we had to with step indices, we will have to prove monotonicity. But the shape of the monotonicity lemma roughly will look something like this. If V, in the current world, where we have k steps left and the store is a mapping from locations to values, it looks like it has a certain shape. Then in the future, when you may have updated the store S to some new store S prime, which means you might have taken any number of steps from, when you have k over here, in the future you might have j steps left. Somewhere in here, you might have done a whole bunch of updates to the store. So your S over here changed to some S prime, right? There might be a location L. It contains a Boolean. Maybe you went and updated it with a function. How do I prevent that kind of thing, right? The way that I constrain updates, so before, we were moving from a current world to a future world by saying, in the future, we always have fewer steps left. Those are valid future worlds, where the step index goes down. Now we have to say, what are valid future worlds, given that we are sitting in this world and the store looks like this? And basically what we want to say is that this store can evolve to this other store in two ways. You can always allocate more memory cells. So we need to say that formally in the math, right? What does it mean to go from current world to a future world? That future world, the domain of S prime can be larger than the domain of S. That's one thing. It allows for dynamic allocation. Number two, we want to say that updates are okay. So for all the locations that currently exist in S, their values can be updated. But we need to say that they can only be updated with values that have the same type as the original type. But nowhere in this world am I keeping track of the original type, so how am I going to say that? Does that make sense? That is why we need the store typing. Otherwise, we cannot say how we move. We can only move to future worlds in a very constrained way with type-preserving updates. So we need to give ourselves the information in the model to just be able to specify that constraint. Okay? I know there are hands going up, but let me just wrap up that thought. Therefore, I am going to do that by not even keeping the S's in the world, because I claim, for now, just believe me, that the S information is sort of subsumed by the information in the store typing, and I'll show you how we connect them later. So instead, what I'm going to keep around is the current, if V belongs to tau in the current world, where my store typing tells me types for all my locations, then in the future, I can go from k psi to a future world j psi prime, where j is smaller than the k. This psi prime can have more locations than the original psi, but for every location that was in the original psi, their types must be the same. The mapping must remain the same. And we'll specify this formally in math in just a minute. So if those constraints are met, then V still looks like it behaves like a tau in the future world. All right, yes,
yeah,
question?
Naively, I'm just wondering, why can't we store the type in S?
Okay. I guess you could do that, but that's kind of like changing the operational semantics. It's just, you would have to go in, formally speaking, what you'd have to do is you'd have to go and update the way that you've specified your operational semantics. We call that an instrumented semantics that keeps around some additional annotations that you need just for your proof structure. People often do this when they do progress and preservation proofs because they need that additional information. But you don't need to. You can just keep it in a separate place. I think that, yeah.
I feel like would it be possible to circumvent this by assigning a type to my assignment operator?
Assigning a type to your assignment operator. So doing something here to the syntax of assignment?
Like assign that into type, and then my step index is
Yeah.
say, okay, whenever I'm doing this assignment,
Uh-huh.
somehow I'm keeping the type.
So I would say that the assignment, at least as far as the typing rule is concerned, even if it's not the syntax, right? The typing rule is making sure that we only update it with taus. That's not the problem. It's just that here, the problem is that in the E relation, what do we say? We say some expression E belongs to the E relation at type tau, or behaves like a tau. I didn't put that up. I should put that up. If, you know, if you run E and it reaches some irreducible term, let's do that actually. I think that's going to be very informative. Let's try to write down, take our E relation from yesterday and try to scale it up. So we had this with a step index k here yesterday, right? And we basically are saying that E behaves like a type tau if for all E prime, oh no, we need a for all j less than k, if for all j less than k, and for all E prime, if E reduces to E prime and E prime is irreducible, then that E prime must be a value that belongs to the V relation at type tau for the remaining, sorry, this should be j, k minus j steps. Right? Let's try to put our s's in. What are we going to do? Now we need to run this. It's an E. We can't run E's alone. They need their stores. Right? So step one, where's the store? Do I put the store here? That's one option. That was our first naive option. If so, then I would have to run with that store. So let me just sprinkle some s's in there. If I run from SE to some S prime E prime, then what? Okay, then the state S prime E prime is irreducible. Now I need to show that the E prime is in the value relation for k minus j in the new store S prime. Isn't that a perfectly good naive extension of what we, it's a good first try. Let's see what would happen. Suppose we'd just done this, and again, we have no psi, we have no store typing. What's happening? You're running the expression, right? I want you to think about programs which have multiple sub-expressions, because you're going to have to prove properties about them. Here's one such thing, application, right? You run E1, when it gets to a value, then you run E2. Somewhere in your proofs, therefore, you're going to be saying, oh, I have E1 in the E relation, what happens? I have E2 in the E relation, what happens? Right? That kind of thing. So I'm just going to hand wave about this a little bit and assert and try to give you a hint of where things are not going to work out. Basically, what's happening is that as you're running your E1, are you, or maybe your E2, are you updating the values stored in locations in a way so that they no longer contain the types they had to? If you are, then there's nothing, I mean, if you change, this is an arbitrary set of changes, right? This is the operational semantics. Running a program has nothing to do with this typing rule at this moment in time. These typing rules are about, oh, you have some program? It type checks? Let me prove to you that nothing will go wrong. All updates will be type preserving, et cetera. But when we're over there, right, doing nothing but running the program, we do not know that this language supports type preserving updates. We want to carry that property around as an invariant, and right now we're just not doing it. We're saying, go run. Okay, you went and ran for a while. Maybe you're running this guy down to some sort of location, and maybe later you're running this, but it goes and updates the location with a value of the wrong type. And maybe then you try to read out of this location later in the program, and oops, you thought you were going to get an int arrow in function, but instead now it contains a Boolean. Basically, these definitions are very local. They're about running little expressions. But we need to know that when we run those little expressions, what are the invariants that are preserved so that the other parts of the program know that they can rely on those invariants. And the big invariant that we're missing right now is that the updates never change types. Programs run. Pieces of program run here and there, right? Little sub-expressions all over the place. But when they run, they never change the type. That's the invariant. We haven't baked that invariant into our definition unless we start to carry around a store typing that forces us to show that that invariant is preserved. Yeah?
I just want to make sure I understand. Why can't we embed into the set relation information about how S changes, that it can only be updated with a new heap location, or that the current location can change the value but not the type?
So you want to build that into the reduction relation? Or, let me try to summarize the question.
S doesn't contain information about the type.
S doesn't contain information about the type, yes.
Yes.
Yes. Right, I want you to think about the operational semantics as running essentially kind of untyped terms, right? Because what does it have to do with the type system? It doesn't really. And then you type checked these untyped terms, and you came up with a typing derivation, and now you want to show that a consequence of type checking, of the fact that you are able to construct a typing derivation, means something. It means absence of stuckness. Yes?
So we have like relations for values, for expressions, for substitutions. Why are we choosing to like index by these stores and not have like a store relation? I guess is that possible?
It depends how you formulate things. Okay, so let's see. Where would a store relation come from? Let me take that point, digress slightly. Notice how my type checking rules don't have a store typing in them. Whenever you do, if you have done a proof of type soundness using progress and preservation for a language with references, there's a chapter in Benjamin Pierce's Types in Programming Languages, which does just that. You will see that Benjamin's typing rules do not have the shape under gamma E has type tau. Instead, they have the shape under a store typing psi. I think he writes sigma, but whatever. And a term environment gamma, E has type tau. Why does he need to do that? Because one of the terms that he needs to type check when you're doing a progress and preservation proof that you need to type check is running terms. So you need to be able to ascribe a type to a location L. Remember yesterday I said I don't need to type check running terms if I'm using semantic type soundness? So that's why I have not added any size here, but if you're using progress and preservation, you need to type check running terms. Locations only get created when you start running programs and you do a new. Before that, the programmer wrote down a program, there are no L's in it, there are no locations in it, right? You write down new something. It's when you start running that the new will produce a location, right? And then if you're using progress and preservation, you need to type check running terms, so I need to type check the L. What is the type of the L? Where am I gonna get it if I don't have the psi? Right? There's just no way. So that's why you put a psi there. You say psi tells us what our assumptions are about the types of all the locations. And then we say, okay, so if I go look up L in psi, I'm going to get a tau, and that tells me that L must have type ref of tau. That is a typing rule you will need to do. You will need to add if you have to type check running terms. I haven't done that. So back to your question. If I were changing the shape of my judgment so I have size, then yes, in the model, I would give an interpretation to size. But even then, it doesn't answer the question of how do we ensure that the invariants are preserved. We need to do something here, okay, in this relation. This relation, the E relation, is about what happens when we run. We are going to have to run with stores. The store is going to have to change. But what we want is to be able to constrain that change and say, that whenever you run any part of the program, types are not going to change. So here's how we're going to try to do that. Not going to put the S there, okay? So it's going to come out of here, going to come out of somewhere, right? Instead, I'm going to say my world keeps track of the current step index, how many steps I have left, and what my current store typing is. So in other words, I'm keeping track of all the locations that currently exist in memory, because that'll be the domain of this store typing, and I'm keeping track of what types those locations should contain. Now, when a program runs, what happens? Okay, we don't have an S. So I'm going to start us off by saying, give me an S. Give me any store that satisfies my store typing. That's easy to do, right? You can give me a store that has mappings for all the locations L that are in the domain of this guy, and the values that it contains, the values at those locations match the types that this tells us they should have. Okay? So I'm going to say for all S such that S satisfies psi. We'll formalize this later. Let's say for K steps. I've just said in English what that should mean, right? And we'll formally write it down in a minute. So first I have to pick an S, because then I need to run with that S. So SE runs to S prime E prime. Let's put some for alls here. So for all S for all S prime, for all E prime, and we also need a for all j less than or equal to k. First, pick a store that satisfies the store typing for the remaining number of steps k, because that's how long we need to run. Go ahead and run for some j less than k. Okay. If you've reached an irreducible state, I'm just going to write it here. I'm running out of space. So irreducible S prime E prime. Then what? Then a few things. Then, sorry, this thing is here. Then it better be the case that whatever store you end up with satisfies some future store typing, right? Okay. So I'm going to say that there should exist some future psi prime that is such that j psi prime, no, not j. How many steps do we have left? We used up j, so it's k minus j. So for the remaining number of steps, k minus j, this psi prime looks like it is a valid extension of k psi. What does that mean? We were in this world before we started running. You are allowed to go to this world. Your step index is allowed to go down. That's what this relation will say. For the domain of your psi, all the locations that were in here better be in the domain of this. But this can have a larger domain because you're allocating more locations. Furthermore, for every single location in here, if it was equal to a v tau, then over here, it's still equal to the same v tau, but to a lower approximation for fewer step indices, because you ate up some steps. That's what this future world relation is saying. So you better be able to construct a future psi prime, and it better be the case that the store that you ended up with, this future S prime that you evaluated to, it satisfies your future psi prime for the remaining number of steps k minus j. Okay? So I got somewhere. That thing better satisfy a store typing that is good with respect to the original one. New store satisfies new store typing. And finally, the E prime better be a value. Better be in the V relation at type tau for the remaining number of steps k minus j, and in the new world, the new store typing, psi prime. Sorry, that's a lot. I know that's a lot. Yeah.
I have a much more adjacent question, but
Yep.
you brought it up.
Okay.
You talked about the application relation.
Yes. It was a hand wavy kind of attempt at trying to explain why type preservation needs to be enforced. Yeah.
We probably discussed this in the operational semantics part yesterday.
Mm-hmm.
Do we have a defined order evaluation? Like,
Yes. Order evaluation is still very much deterministic. Remember yesterday when I was doing recursive types even, I said, oh, order evaluation is deterministic. The only thing that's non-deterministic now is that when you allocate a fresh location, you get to pick a location name of your choice, as long as it's fresh, right? But that doesn't really matter. Order evaluation is still very much deterministic.
so when you evaluate E1, the new state from E1 passes to the beginning of the evaluation for E2?
Yes. Exactly. When we run this, what's going to happen is we're going to start running in a store S. It's going to, in some number of steps, get to some, let's call this S0. It's going to get to some S1 with V1, E2 there. And then you're going to run for more steps. It's going to get to some S2 with V1, V2 there, et cetera, right? And then you're going to keep going. So the store keeps evolving. The values keep getting passed on. Yes?
Just two really fast questions. One, I noticed you changed J strictly less than K to J at most.
Oh.
Does that matter at all?
No, sorry, mistake.
So why is it strictly less than theirs and then at most in the
Okay, so that's exactly what I did when we had recursive types as well. So I'm not changing anything from that lecture. It's strictly less than here. So here it doesn't need to be strictly less than. Why? Because I don't need it for my induction metric, basically. I'm defining the meaning of tau 1 or tau 2 by referring to a smaller type tau 1 and a smaller type tau 2. And if we go look at the tau 2 there, it's basically referring only to b of tau 2, right? So that's why the less than or equal is totally fine. Here, j has to be strictly less than k. In a sense, we do that to say that, to have it work out so that at 0 steps, every expression behaves like a tau, no matter what the expression is. And so this just sort of automatically lets us do that, because if this was a 0, and then I ask you, I say, give me a natural number, because this is assuming j is a natural number, that's strictly less than k, well, there isn't one, so you don't need to prove anything about it. So any expression will end up being in that relation without doing anything, without inspecting it in any way at all.
Okay, and then could you just briefly recharacterize the relationship between psi prime and
Yes.
psi?
Okay, so in my current world, psi is telling me what are all of the locations in my store. Okay, so psi is telling me some information about location L1, L2. Maybe we just have 4 locations. Okay, what is it telling me? It's telling me what are the types that are stored there. Okay, v of tau 1, v of tau 2, tau 3, etc. Maybe these are both tau 3. Okay, in the future, what are the future store typings that I can move to? In a language where I only do type preserving updates, every single one of these locations, and I can't free anything, right? We don't have a free construct. So I can allocate more locations. So any future psi prime that I can move to can have more locations. It will still have L1, L2, L3, and L4. It must. It must, right? Because we are never freeing locations. It's type preserving updates. And because it's type preserving updates, these types must remain unchanged. Okay? So these will be exactly the same as those. They will be equal. That's one property. But this can have more things. It can have an L5. It can have an L6. Because in getting from here to here, you may have done some allocation. And we say nothing about those types. You have your choice of whatever you want to put in, initialize those new cells with. Okay? So in the future, we can move to store typings that are bigger. But whatever store typings we move to, for all the locations that existed in our original psi, they still have to contain the same types. Okay? Those are, yeah.
So I noticed in the E relation, we're
Yeah.
indexing over K and psi.
Yeah.
And then in the V relation, inside the E relation, we're indexing also over, well, the step index and psi,
Yeah.
psi prime. But then right above it, we have a triply index V relation.
That's because I never finished editing that one.
Oh, okay, okay.
I was going between 2 different ideas or proposals. So let's start to clean that up. Okay? Yeah. Good?
Yeah.
I haven't finished yet, because that's wrong. Okay, so now we're going to say that our world is a K and a store typing. So when does L belong to ref of tau? This isn't here. There's no S. I can't even refer to it, right? So basically, all I want to say is that second condition. L behaves like a ref of tau if the store typing tells us that L should contain a tau. Okay? I am going to restrict this store typing. Think of that as restriction. Okay, these floor symbols. I'm going to say restrict it to a lower step index, k minus 1. And then I want you to take this notation to mean that, this guy needs to be restricted as well. But I need a minute to get there. For now, just think of it as L says it contains v taus, right? So how are we getting the other condition that when you are in a store and you try to read out of it, it will always contain that? Well, we're doing that magic over here, right? When we start running something, we say, oh, give me a store that satisfies the store typing. And that will immediately mean, I haven't shown you the definition of this yet, but the definition of this will say, for every single location in the domain of the store typing, go and look up what is stored in the store. And whatever you get, the value you get there, right, S of L, whatever S of L you get, it better belong to whatever psi of L maps to, in essence. And again, sorry, I'm sort of getting there slowly, but intuitively with a lot of informality thrown in. I haven't shown you the circularity yet. Okay, yes.
Just to be clear, are we pushing this for all S into the V, or is that like implicit in when we put it to S?
When you say pushing, where do you mean?
So in V, we don't write this for all S and psi. Is that because we don't have to, write it in E, or do we also need to have a for all S somewhere?
No, we don't need to write it in the V's at all. We only need to talk about it when we start running the programs because we need the S to run the program. Yeah. And I have a story here. The very first time, so this is the stuff that's in my PhD thesis. And when I was a grad student, the very first time we submitted a paper on this, I actually had a model, we had a model where we did have KS psi. And we pushed the whole thing through, it was fine. It was just one of the very, very astute reviewers, I remember we submitted it to LIX, a very astute reviewer said, you know what? You probably don't need to put the S's in the view relation. It's probably enough to just have them here. Reviewer was right. So we simplified it. It means your proofs get a little shorter because your math is, your definitions are a little shorter. So yeah, this is the better model, more succinct. Yeah.
So when you said that there's no free, does that mean that the rules of the system only ever allow you to have space?
So in languages like Java and ML, you have a garbage collector. Yes. And so, there's no construct that a programmer can ever use to free memory. So the model basically acts as if memory only ever grows, and then you assume that the garbage collector is doing the right thing under the hood, but you'd have to verify it, et cetera, et cetera. Yeah?
What is different between the value relation indexed by numbers and value relation unindexed by but restricted?
You mean right here, when the reduction relation? No, you're talking about the value relation.
Yes, so in this ref case,
Yeah.
it says that psi of L is equal to restriction of value relation
Yeah.
minus 1.
Uh-huh.
What's the difference between this notation and V index K minus 1?
Okay. I need to do a big digression and we'll come back. Okay, because I have not defined, you're absolutely right, I have not defined this yet. I'm asking you to sort of say that, assume that it's somehow smaller. But, okay, let's come back to it. So let's talk about what's going on in this model and where the circularity is. So remember yesterday, I wrote a bunch of kind of meta types for what our type interpretations are in the first two models that we constructed. So I think I wrote something like type in STLC was a set of interpretations I, where I was basically drawn from a power set of closed values. I'll just write cval. Okay? Because that's where every type every v tau was a set of values, closed values, right? So I'm saying if a v tau, those v taus are i's, I'm using the letter I to represent them, okay? And those were just sets of closed values. So they were drawn from the power set of closed values. Then when we added recursive types, type interpretations became a function, really, from nat to sets of closed values, right? Because I started writing these guys as, instead of v tau, I was writing, oh, give me a natural number, and then I'll give you this thing. I'll give you the set of closed values. So at a certain index, I will tell you what values inhabit the type. What are we doing now? What are we doing now? Okay. We're doing something like type interpretations. Give me a nat, and give me a store typing. If you give me these two things, then I will give you back something that is a set of closed values. Okay. Oh, by the way, there's another property here. Like, really, we should say that these i's have the monotonicity property, but I'm just not going to write it out. Mathematically, you would say that whatever this, it's basically monotonicity, right? If I belongs to, sorry, if a v belongs to I for k steps, then the same v belongs to the same I for fewer steps, okay? Here, what is this store type? I have to say, right? I haven't said yet. Okay, so a type is that. A store type is going to be, what have I said? I've said it's a mapping, a finite map from locations to type interpretations. So to things I that are drawn from this space, right?
Oddly recursive.
Sorry?
It's oddly recursive.
I don't know who's talking. Oh, there you are. Okay. It's oddly recursive. Yes. How oddly should we worry? What? It's like, let's just talk about what's the cardinality of these two sets? All right. What are these equations telling us? So I'm going to write type, cardinality of type. This thing is telling us that the cardinality of type, because store type appears in the negative position of this function, the cardinality of type has to be strictly greater than the cardinality of store type, right? Okay. Now, if we look at this one, type appears on this side, so the cardinality of store type must be greater than or equal to the cardinality of type. Yeah. Good reaction. Oops.
I assume we should be in store type annotating it with some natural number.
Yes.
Saying the type is less.
Right, exactly, right? This cardinality thing that I did isn't like taking the nats into account, but then right now, if we just think of this naively as a mapping from locations to types, then we haven't done anything to stratify. So the answer is yes, we need to stratify it somehow, this whole type and store type hierarchy, right? And the way that we're going to do this is basically by leveraging the step indexing insight. And this goes back to what I said earlier. Step indexing ended up being remarkably useful for solving all kinds of circularities, not just the first simple one with recursive types, but even this really nasty one. Okay, so let's talk about how we're going to solve this. I'm going to just delete the top parts and write over there. So what we want is a sort of stratified set of types or a hierarchy of types. I'm happy with saying that type at level 0 is just the empty set, doesn't have anything. But then I want to say that type at some level k plus 1, it should take, I'm not going to write it as I and set of, I'll just write nat. Give me a nat and a store typing. But now, for type at k plus 1, I want a store typing that comes from level k. Okay, and I'll define store type at different levels in a second. So if you give me that, then I give you back a set of closed values. Okay, and now we still have to say what is the store type at level k. Store type at level k is going to be a mapping, finite map from locations to types at level k. With that, we break the circularity. So type 0, you can take type 0 to build a store type 0. You can take a store type 0 to build a type 1. And then you can take the type 1 and build a store type 1. And then you can take the store type 1 and build a type 2, etc. Okay, so we have stratified it. Now we do not have a cardinality problem. But we do need to figure out how to ensure that whenever we have a certain nat here, how does it correspond to the store type that is sitting with it? And I'm also going to start calling these our worlds, which I have been doing loosely. But I want you to think of this as a world at level k. Okay? And more formally speaking, yeah, I'm just going to shove the step index into together with the store typing to say that that is the world. Okay? So let's go here. Now it's starting to get really kind of hairy. If you want to stop me, ask questions, please do. But I'm going to just sort of try to give you as much intuition as I can about the math that follows. All right, so what we're going to do is I'm going to start defining a world, n, as w's that are pairs of these k and psi, such that k is strictly less than this n. So when I define a world at level n, the step indices that sit inside that world must be strictly less than n. Okay, now I'm trying to like take these tuples and like really stratify them properly. But furthermore, the store tie that sits next to a k has to be bounded by that k. All right? So I'm going to write that as psi comes from store type at k. Okay? And what is a store type at some arbitrary n? It's going to be a psi that maps locations to types at level n. What is a type at level n? It is some interpretation I that given a world at level n, so type at level n takes a world at level n, which, by the way, contains only step indices that are lower and size that are lower than the n, strictly lower, right? K strictly lower than n, and gives us back closed values. And then this time I'll be more precise. These types have to have the monotonicity property, so let's write that down. We're going to say for all, they basically need to have the property that given, loosely speaking, if some value belongs to I in the current world, then it belongs to it in all future worlds. But I haven't given you the future world definition yet, so let me not complete this part quite right now. So I'm just going to write this as monotonicity property should hold for the I. Okay? Should I pause? That thing that I just did on the board is about just making sure that you are drawing things from the right spaces. You see why we had a cardinality problem, and therefore we had to stratify our type and store typing in order to avoid this. We call this the type world circularity. It arises when you have dynamically allocated mutable references. Okay? Some people will say it's the problem of higher order store. When you can store functions into the heap, this problem arises, and you have type preserving updates. Yes?
Sorry, for the definition on the left, is that just like type K and the net is just K?
Sorry, louder?
So for the definition on the left, is that just type K and the net is basically just K, or am I mistaken?
This one right here?
Yeah.
This is type at level k plus 1 is defined as something that takes a nat and takes a store type at level k. So this k is smaller than this k. So in order to construct a type at level k plus 1, you need to give me a store type at one smaller level. This is how we're breaking the circularity. A type can never depend on a store type at the same level. It must draw upon things at a lower level. Yes?
Could you also break this specific circularity by saying that a store type maps to a syntactic type instead of a semantic one?
You perhaps could, but then it wouldn't be. Oh, the question is, can you break the type world circularity by having the store typing psi map locations to syntactic types instead of semantic ones? Perhaps, but then it wouldn't be a semantic model. And I don't know exactly where something would go wrong.
But you could, the way where you actually need it is when you define the V of the reference.
The V of the reference type.
This is where you could use, because I guess all the inputs for the V's are syntactic types, right?
Yeah, yeah.
Here you could feed your syntactic types, but then compute the semantic interpretation at this point.
Yeah, let me sort of say that being able to put semantic type interpretations in there gives you more power, because sometimes you may not even have certain syntactic types in your system. So this gives you more generality in if you want to extend your language with other features, if you want to bring in unsafe code, etc. Because you may not even have certain syntactic types in your language, but you might be able to construct the sets of values that correspond to those types that don't have syntax in your system. And then you can, your store typing psi can keep track of all of those semantic typings. It doesn't, and things would still work out. So especially when you add polymorphism to your language and so on, these kinds of things become interesting. But it's not, that's a slightly fuzzy answer, right? Yes, Nico. Oh, sorry. Yeah, go ahead.
It's not really clear to me if this is sort of just a, is there a real world implication of modeling it this way? Like, are you requiring that we start with Semantic heap and build something out of only things that already existed, or is it just a modeling?
No, you should think of this hierarchy issue as just something that is about the model. We want to make sure that we are inductively constructing these sets so that we never have to go off and do the really, really crazy hairy proofs about, oh, the sets that I wrote down are actually inhabited, or the relations that I wrote down are actually inhabited, because that stuff is really bad to have to show that. And so if you define everything inductively, it's just sort of, you can stare at the definition and say, oh yeah, these are all inhabited, this is all well-founded. And therefore, when I do proofs by induction, it's all going to make sense. So that's the advantage. Avoids a lot of proof about your definitions.
These Ks are not the same steps that we're taking as we walk through it.
Yes. So, there's this funny game that we've been playing. Are these Ks the same as the steps? I like to explain them as if they are, because the intuition ties up really nicely with what we're doing in the E relation. But strictly speaking, I've been saying this in prior lectures, that you can play a game with which steps you're counting, right? Because at the end of the day, what you're trying to do in the semantic model is break the cycle. And the cycle occurs at reference types, and it occurs at recursive types, okay? So so in our new extended language, the steps that you need to count, if you had an unfold of a fold, you need to count that as a one step, because recursive types have a circularity. And you need to count new, dereferencing, and assignment as one-step operations. Every other operation in our current language can be treated as a zero-step operation. So basically, it's a semantic trick that's giving us induction in just the right places so that we have a well-founded model. So it is connected to steps because because at the end of the day, the E relation is talking about steps, and the operations that cause the genuine circularities, we want to count them to get our induction metric. But that's the only thing, So it's somewhere in the middle. Yes, I'm so sorry. I've been.
No, that's fine.
Yeah.
That's fine. I see that world always relies on the previous world. I don't see anywhere the base case for that though.
Okay.
Did we define it somewhere?
So world 0 would have to have lower step indices. So that doesn't really exist. All right, so world 1 is the first one that you can actually have that's non-empty. So basically what this definition means is that world 0 is empty. So I can define it. I can write it down. It kind of falls out of the definition due to the K strictly less than N. But basically what that means is world 0 is empty. Okay? Yes?
So this is like a stratification of like the semantic types. But if you have like syntactic type universes, like is this handed to you? Like it already kind of stratifies like your induction.
In a model like this, or in a different style of proof?
I guess I'm not sure. Like in a language where you have type universes.
Where you have type
It feels
universes.
like you're just, like,
Oh, type universes as in, yeah. So like independent types or something where you have universes. Computer scientists use natural numbers a lot to do induction and stratify things. So I think that is just a coincidence. Their universes are doing a similar sort of trick that, it doesn't, because you have a circularity, it doesn't really make sense, right? Set can't be in set type of thing. So, we end up stratifying to make sense of the world in some sense. And this is just another form of stratification. They look very similar because we appeal to this kind of thing all the time. Yeah.
Can we go back to the top level to state our theorem about type safety?
Yeah.
Is the K going to be existentially qualified, for any given program there existing?
At the very, very top level, what we've been doing is under gamma, E has type tau, right? Sorry, double turnstile. And that is defined as for all K greater than or equal to 0, you have to prove to me, until yesterday, today we have to change it, you have to prove to me that for all gamma that belong to G gamma at K, it must be the case that gamma E is in E K tau. So let's see what we have to do here. We have to say for all k greater than or equal to 0. We also want to say for all psi. We then want to make sure that if you've decided to be in the k world, then this combination of k and psi better be, properly stratified and better belong to a world at level k, or k plus 1, I guess. Because I've written n over there, so I'll just write it as this thing is something valid that comes from world k plus 1. I'm putting the k there. Okay, so this alone is going to make sure that these guys come from the right level, right? They're going to be store typings at level k and internally contain things that get smaller and smaller. Okay, so then we pick that. Now we have to say, give me, let me just put my for all gamma somewhere. Give me a substitution that belongs to G of gamma in the world k psi. And you know what this is going to do, right? It's going to say every single value needs to belong to V tau k psi. Okay? If you give me a substitution, then it's pretty easy. I'm going to close off my E, and it's going to belong to the type tau in the world k psi. So it very easily generalizes. Just a little bit of care required because we are selecting a store typing. It has to be at the right level with respect to the k, so it must be in this world k plus 1. This ensures the stratification is good. This part ensures that when you go and start picking values for your substitutions, that those values, right? So let's write that down. So we picked the psi out of thin air right here, but now we are using it to do some value selection in our G relation. What does that mean? Well, basically, when we say any substitution like this is okay, what we're asking for is that the easy part, the trivial part is this gamma substitution needs to satisfy that gamma, but then the interesting part is that the V needs to satisfy V at k psi tau. And what that is going to do is that somehow this is asking that whatever value this is, this psi has to be sufficient for it. So suppose that the value that you were picking has something to do with references or locations. That means you'll end up going, into that part of the definition and looking up appropriate things in the psi. Okay? So if I had some x in here that had a type ref tau, and what I'm trying to give you as a value for that ref tau is a location, what this definition will end up doing is asking that that location belong to that type ref tau, and then that definition will demand that this psi contain that location. Right? So that's how all of these things get tied up together. And even though we're picking an arbitrary psi, we're making sure it's enough for all the substitutions that you are about to give me. If your substitutions talk about any locations whatsoever, all the definitions that you're going to drill down into to make sure that those values are of good types or well-behaved in those types, they will insist that the psi talk about those locations and say that they have appropriate types. Okay. Yes?
How about exist actually quantify psi prime in the definition of the...
Yes.
Does that need the world thing?
Does that need the world thing? In a sense, it has the world thing because I haven't finished my definitions yet. So you're absolutely right. Here we say there exists a psi prime. It will be the case. What I'm saying will be the case will be a consequence of this definition, but it will be the case that whatever this psi prime is, it will belong to store tie at k minus j. This definition will make sure of that. Okay. I think I'm not going to get past mutable references today. But this is fine. Yes? Wait, say that again. What is the difference between the capital T type?
What's the difference between or relation between the capital T type and the logical relation?
Excellent question. Okay. So what is the difference between this capital T type, the bad one that I created, and the good one, right? And like what's happening in the logical relation. Basically, at the end of the day, after you write down all of your v tau relations, technically speaking, one of the things you should show is that every single v tau indexed by k psi that you defined belongs to TYPE at the appropriate level. Okay? Or if you say that, okay, another way of so normally we write down types indexed by all of that, and then at the end, somewhere in the paper we'll say, oh, and type is equal to the union for all k greater or equal to 0 of type k. In other words, we're like, okay, now I'm just going to squint and not think about the actual level of type that you're drawing from, okay? But even so, this type is coming from something that we built. It's fully stratified, very good structure, okay? Here we're just saying, there exists a k, in a sense. So now what do you need to do? One of the things you need to do is show that every single v tau, given a k and a psi that come from, let's say, some world n, where n is greater than k, you need to show that it belongs to type. In other words, these things are exactly these I interpretations, the sets of the right shapes that belong to these semantic objects that we're trying to construct, right? This type stuff are sets of interpretations, semantic objects that the types are going to become. Because they're no longer just sets of values, they are now sort of sets of triples in a sense, or functions from Nat store type 2 sets of values. They got more complicated. You can think of them as tuples of k, psi, and values. But let me finish that thought. Why am I saying that you have to prove that these V interpretations belong to type? On day one, when we were doing STLC, they were just so trivially, they belong to type because types were just sets of closed values. We could look at those sets and say, yeah, of course, they're sets of closed values. Yesterday, when we had step-indexed relations, but no psi yet, suddenly I had a property I needed to prove. It was called monotonicity. Because yesterday, our semantic type objects, remember I keep writing mono on the side? I've erased it now, but I was writing monotonicity on the side. Basically, anything that belongs to capital TYPE type yesterday had to have, that interpretation I had to have the property of downward closedness or monotonicity. Otherwise, it's not a valid semantic type. That's why we had to prove that monotonicity property lemma, and then we end up using it in proofs of the fundamental property for various cases. We used it for fold. Okay, that's the connection. So basically the game is you're defining type interpretations. You start out in a very naive way. You say, okay, what's my intuition? How do I use something of this type? What should my definition say? All right. Then there are some technical conditions that arise. If these are possible worlds models, you're going to end up needing some sort of monotonicity. So then, mathematically speaking, you're constructing objects which have certain properties. Here it has this monotonicity property on the side. Well, that's the bad one, but the good one has the monotonicity property on the side. There. So that means that when I construct my v taus, I need to show that they are good. They are, good or valid semantic types, which means not only do they have this structure, which you can sort of see just by observing the definitions, but they also have the monotonicity property. Okay, now, said enough. Let's write down the actual monotonicity property, or at least get to a point where we can. What have I not defined? There are many parts of this that are missing. I still haven't answered the question of how am I approximating this and getting to the right level. Okay, but let me do that just a little bit loosely for another minute by saying, basically what I want to do is I want to take this and restrict it to come from, right now, psi of L is going to have in its codomain anything at level k minus 1 and lower. You can look at the definition of world and it'll tell you that. Okay? So when I say go look up psi of L, what I'm getting is something from that level of the universe. So that means that I just need to compare it to V of tau for that level of the universe. Now I can write this either with some sort of floor kind of notation, or I can write it as k minus 1, but then I have to take k minus 1 psi, but I have to take my psi and restrict it to k minus 1 as well. You get the general idea of how I'm going to do that. I'm just not writing that. Okay? I'm just going to more loosely going to write this as a prox. Whatever this set is, feed in the right level. This is going to cut it down to k minus 1. So anything lower than this k, that's what you're comparing. Okay? Drawn from the appropriate level. But the things that I haven't defined, I want to talk about this. What does it mean for a store to satisfy a store typing? And this one's really important. What are the future worlds that we can move to? And then I think we will almost have done everything. How are you guys feeling? All right. All right. Some j psi prime is a valid future world of a current k psi if all the things that I was saying in English, we're just going to turn them into math. If j is less than or equal to k, because in the future you can have the same or fewer steps, but you can't have more steps, right? And if I wanted to, sometimes we do a square bracket less than equal to notation, which is why I've picked j less than or equal to k. Some papers will also have this one without the less than, in which case they'll say, oh, j is strictly less than k. Just saves you a little bit of trouble. All right, so the step index in the future cannot go up. And for all locations in the domain of my store typing, I have to make sure that their types are preserved, right? It better be the case that if I take psi of L, my original psi, and I look up the type associated with L, if I approximate that, so now let me write that as, in a sense, what I'm doing is I'm taking that and applying it, right? Because my interpretation says I can apply it to, I need to apply it to a number, to a world, which is a pair of a number and a store typing. But the store typing has to come from the appropriate level. I can write it as j minus 1 and then psi j minus 1. Or I can write it slightly differently, whichever one you guys feel better about. I'll show you both. In other words, cut this down and make sure that it comes from store type j minus 1. In other words, just restrict it. I think in the interest of like keeping it succinct, I'm going to switch to the notation where I will use these floor notation and just put a j minus 1 there. And that means you have to cut down both things appropriately. Okay, so they come from the right world level. Is that all right? Okay. So go look up the type that's stored over there. Restrict it to j minus to j, and then psi prime of L better map to the same thing. Why am I putting j minus 1 there instead of k?
Because the types themselves are indexed by j minus 1 seems to be
Right. So I mean, at the top level, all I want to say is that for every location that I have in my current store typing in the current world, in the future world, that location maps to a certain type. That type better be the same as what it maps to right now, right? The rest is just step indexing math because things have to be stratified. So what are we going to inspect? What we really care about is in that future when we have j steps left, which means that when we're j steps left, we can look at psi prime of L up to j minus 1. So the set, the mapping psi prime L up to j minus 1 better be equal to the current mapping restricted to a j minus 1. Because we really don't care about what it is now. We care about, in that future, what worlds are valid. The ones that, at that point in the future, they only need j steps. Therefore, just do a j minus 1 comparison. OK? Because those actually should not know anything for k steps, because that would be too much for that future world. Yeah?
You may have already said it. Could you remind me what the floor brackets represent?
I'm trying to say that psi of L is any type whatsoever. Remember, a type is something that says, give me a world and I'll give you sets of closed values. So now what I want to do is I want to give you a world at an appropriate level, and that level is j minus 1.
Okay.
It's my shorthand for saying that. OK. So this is a world extension. This is a possible worlds model. We say that if you're in this world, these are the only worlds that you can move to in the future. Right? And part of what we're doing in the proofs later as we prove the fundamental property, we're going to have to prove monotonicity. Right? In order to prove the fundamental property, monotonicity is going to say, so now let's write down monotonicity. Monotonicity for this language will say that if V belongs to V of any type tau at k psi, and you have some j psi prime that is a future world of k psi, then V better belong to the type, or better behave like the type, tau, in that future world j psi prime. This is monotonicity now. But it's really, really cool now, because it's not just making sure that your type behaves like that in the future, when you have fewer steps left to interact with it. It's also making sure that it's saying that only in good future worlds where you only did type preserving updates, the value still behaves like the same type. Okay? And the beauty of our language is that it has an assignment rule which asks us only to update cells with values of the same type. Right? Okay. Final definition we want to get to is, when does a store satisfy a psi? So store S satisfies store typing psi for k steps. What do you think we want to say here? Have values that have the corresponding type. Yes. OK. So we want to make sure that all the values in here have the types that those locations should have, right? So OK, let's be a little slower. First of all, we could say something about the domains. We can say that the domains are equal, but at the very least, the domain of everything in psi better be in S, right? So I can really make this unequal, but in the interest of showing it to you very, very properly, this is the bare minimum we require, right? Because why do we want that? Because look, we're doing something kind of big here. In the E relation, we're saying, give me an arbitrary store. It just has to satisfy my store typing. So the store typing gets to dictate, what has to happen, right? If the store typing has a location, the store better have that location. So first of all, that's the domain condition. And then we can say for all j less than k, we want it to be the case that for every single location in the domain of our store typing, S of L, the value that we look up in the store, better belong to the right type. Look up psi of L, and better belong to the right type for the appropriate number of steps. So here is where I'm going to restrict to j. The only thing that I did differently from the definition you suggested is I generalized to any j strictly less than k. Okay? That's another thing. When I write S satisfies psi for k, what I really mean is all the values in it satisfy the types in psi up to k minus 1. And my reasoning for that is that if you were to read out of that store, you're already giving up one step. So knowing that you're getting back a value that's good for one fewer step is good enough. That is something that has been thought out, and that is why this is a strictly less than k. And if I wrote it just without talking about arbitrary j's, I would still put a k minus 1 there. It's part of resolving these kind of circularities. Yeah? No, the psi is what tells us all the locations that are required. So if the store has more junk, I don't care. But it better have every location that the psi is relying on, right? Because over here, we start out and we say our world is described by psi. So all the locations that psi says we must have, we must have. I mean, I can make this easier by just saying equal.
Intuitively, psi describes the state of the program.
It describes the state of the program, so the program better have those locations. But again, equal is totally fine. Everything will work out. In fact, in some sense, it's easier. You don't have to think too much. Yeah? Monotonicity is something you have to prove about every single V relation interpretation that we wrote down. So yes, this lemma is something we have to prove by induction on tau. And we will have a case for Boolean, a case for function, and a case for ref. You know what we didn't do? We didn't edit our definition of functions. That's a cool one. It should be straightforward, though. You guys should just be able to guess what it is. Let's do it here. I put it up there. Should we edit it up there? Let's just write it out again. Okay, so k psi, tau 1 arrow tau 2. By the way, for Booleans, nothing happens, right? I'm just going to put a psi there, and we're done. But this one, we'll edit over there. All right, so when does a lambda x colon tau 1 dot e behave like a tau 1 arrow tau 2 in this world where we have mutable references and updates? What do I need to do? You have the other one here. Let's just remember the English, right? Lambda behaves like this if in the future, if at some point in the future you give me an argument that behaves like a tau 1, and I plug it into the body, and this behaves, what was this? Yeah. This behaves like the result type tau 2. So how do we do future here? Current world is k psi. Yes, Vadim.
So for all j less than, I'm not sure if we need to show there, less than 8.
Yeah.
We want a value from bj psi.
Like that?
1.
Ah, psi. Psi is the current psi.
Oh, so we need some psi prime which satisfies the current psi, which is
Yes. Some future.
future
right?
psi, which is
Exactly.
in the future world, so we need the relation from future.
Let's write it like this. For all j, for all future j, comma, psi prime, that is a valid future world of k psi if v
from
j psi prime.
at tau 1,
Mm-hmm.
if we do a substitution into it behaves like j psi prime tau 2.
Why does this work? Because the English is the same as the other one. All right? You just have to move to a valid future world. That's what we were doing all along. We said, lambda behaves like function type. If at some point in the future, it's just that some point in the future is one where we have fewer steps left, the value is good in that future world, then plugging it in is good at the result type. Same thing. For any future world that is a valid future that we can move to, from k psi. If you give me at that point in the future, in that future world, a value that behaves like a tau 1, then from that future world on, plugging it in will behave like the result type tau 2. Future world intuition is really great, and I'm explaining it to you that way because if you go off and construct your own models with your own futures, you know what to scale, right? You might have a world which has more elements in it because it's keeping track of an extra thing. In fact, that's what I want to show you next. But you'll know that this definition generalizes like that just by saying, oh, future world, right? Another trick that we often use for it is we started writing worlds as just W's and W primes, right? And then you don't even have to think about what the internal ingredients are. The definition looks identical when you, even if you change the world structure underneath, as long as you define world extension or moving to future worlds properly. By the way, in possible world semantics, this thing is often called, this relation, going from a current world to a future world, is often called an accessibility relation because it's about what future worlds are accessible from the current one. And all of this comes from models, originally possible worlds model. That idea comes from models of modal logic invented by Saul Kripke, and that's why they are also called Kripke models. So possible worlds models and Kripke models are the same thing. They have this idea of a future world and an accessibility relation. I'm just telling you all the terminology that you might encounter if you see these things. Yes?
Just to check an understanding of monotonicity, is that exactly enforcing that your accessibility relation, your Kripke semantic, is transitive?
The accessibility relation will be transitive. Yes.
Is monotonicity the thing that's enforcing that?
Ooh. Well, if you're strictly interested in transitivity of this relation, then you can just prove it as a separate lemma, so it has nothing to do with the monotonicity lemma. But yes, the monotonicity lemma, I think, will only be sensible for accessibility relations that are transitive. That's what I would say. More questions? Yes? Okay. It means pretty much the same thing as what we were talking about before, that you have, right, what has changed is our idea of a program configuration, right? For any language, when you define how do you run programs, you say, well, what's all the program state that I need to put in my tuple, so to speak, in order to run the program? In languages like simply typed lambda calculus, where you have no state and no heap, right? You just say E is my abstract machine, so my abstract machine takes a step from E to E prime. When we add a heap or a store, we have to say my abstract machine is not just the actual syntax of the program that I'm trying to run, it also is allocating some stuff in a store. So my abstract machine or program configuration, these are all interchangeable terms, it looks like this tuple needs to keep this information in it, and therefore it steps to S prime, E prime. Okay, so then what does it mean for any E, earlier it was E primes that are irreducible because when they couldn't take another step. Now it's the combination of this that is irreducible. One example could be, suppose that I'm trying to read out of a location L, and it's paired up with an S, in the simplest case, is empty. This is an irreducible expression. There is no location. The side condition for the read rule is that L better be in the domain of the store. There's no L in the domain of store. I cannot read it. This is stuck. This is irreducible, right? One example. And there are many, many more examples. Again, true applied to 5 is also irreducible, just like it was before. It just happens to be paired with an S, right? So you might have something like 5 applied to true. Well, you can't apply a number, so this is also an irreducible expression, right? So all the ones before, still irreducible, but now there are more irreducible things because certain conditions might not line up. Like, if the location's not in the store, but it needs to be, then you're stuck. Okay?
If we wanted to add like derived types to our language, or types that don't appear in the typing, do we just need to define B and also show that the type is part of capital T type?
Excellent question. If we wanted to add some derived types or some additional types to our language, what do we need to do? So one of the beauties of this kind of way of proving type soundness is that you can just throw in some extra types, but there's a caveat, okay? So with the language that and the model we have up on the board right now, suppose you wanted to add pairs. Trivial. add the typing rules for pairs. You need a typing rule that constructs pairs, and then you need a typing rule for first and second. Okay, so you threw those in, you threw in the operational semantics, and now all you need to do is you need to write down a value relation for that additional type, and then you need to do 3 extra cases for the fundamental property proof corresponding to the 3 new typing rules that you added. You can do the same thing for sums, right? You go add in your typing rules, you go add in the v of tau1 plus tau2, and then you do the 2 extra proof cases that you added, 3 extra proof cases that you added, right, for each of the typing rules. So it's extremely modular. Now, I say that it's extremely modular and give you these examples, and actually let's do at least one example, the ones that I just said. But notice that my statement is completely nonsense if I'm going from STLC and adding reference types. We just did this, right? We had to change the entire model. So that's the thing. There are certain types that come with a lot of additional structure. For those, you have to change the model. But again, even there, I would say that once you've gotten to a certain level, like with references, most likely you have to change very little because you've already kind of done the bulk of the work. Right? Again, that has been another reason for the success of these kinds of step index models, because very few things need to change. And nowadays, people are defining these kinds of logical relations, these kind of semantic models using the iris separation logic, which, you know, a lot of your work is already done. You don't even need to go back often to the older cases. Yes?
It seems like we can go one step further and kind of generalize our logical relations over like saying, okay, if your type system kind of looks like this,
Yeah.
then, you know, you're learning.
That's a very great idea, right? Like, so it's this desire for a universal kind of model that would work for everything. I don't think there's anything that's universal in the world, so it probably wouldn't quite work. I'm sure you can still dream up something that requires some adjustment. For example, if you start talking about linear types or substructural types, then you might need to keep track of the things in your world in a slightly different way, right? Right now, we have a store typing that's telling us it's doing the work for type preserving updates. But if you start to have type systems like Rust, where you have ownership or borrowing, suddenly you need to keep more information in the world that says, oh, this part is owned. First of all, you move to, like, this is a global store typing. It's telling you about all of the locations that currently exist in Google. In Rust, that's not going to work, because you're going to have to start thinking in terms of local ownership. And then you have to say, okay, so from the perspective of this little piece of my program, these are the locations that it owns, these are the locations that it has mutably borrowed, and these are the locations that it has immutably borrowed. And then you have another sub-piece of your program where you have the same owned, mutably borrowed, and immutably borrowed, and you will need to figure out how to put them together. Owned must be, my owned must be disjoint from your owned. My mutably borrowed must be disjoint from your mutably borrowed. But my immutably borrowed, that's the shared locations, has to overlap and agree with your immutably borrowed. I've described a very different kind of world structure that you need for any kind of substructural type systems that are about ownership and stuff, okay, where you're trying to track resources instead of, those are local in flavor, these are global in flavor. Marco wants to tell us to stop.
I want to remind that we have a coffee break.
That we have a coffee break.
We have another lecture.
And then we have another lecture.
You can tell us more about
tomorrow. Thank you all.